The equipment grounding conductor, or EG, must be sized in accordance with the overcurrent protection device, also known as OCT, protecting the circuit, even if that results in an EGC that is larger than the supply conductors. The reason for this is that the EGC is intended to provide a low impedance path for fault currents to flow back to the source, thereby preventing the development of dangerous voltages on equipment enclosures. If the EGC is sized too small, it may not be able to carry the fault current without overheating or causing a voltage drop that could create a safety hazard. The National Electrical Code, or NEC, requires that the EGC be sized according to Table 250.122, which is based on the ampacity of the OCT. The table shows that for OCTs rated 200 amps or less, the EGC must be sized at least 1/0 AWG copper or 2/0 AWG aluminum. For OCTs rated over 200 amps, the EGC must be sized at least 3/0 AWG copper or 4/0 AWG aluminum. Since the overcurrent protection is sized under 200%, the EGC must be sized according to Table 250.122, which indicates a minimum size of 1/0 AWG copper or 2/0 AWG aluminum. Even though this results in an EGC that is larger than the supply conductors, it is necessary to ensure the safety of the circuit. Let's delve further into the specifics of equipment grounding conductors and the requirements outlined in the National Electrical Code. The primary function of an equipment grounding conductor is to provide a safe, low impedance path for fault current to return to the source. This is crucial for the operation of overcurrent protection devices like circuit breakers and fuses. When a fault occurs, such as a short circuit between a hot conductor and a metal enclosure, a large current flows through the fault path. The equipment grounding conductor facilitates this current flow, allowing the overcurrent protection device to quickly trip and interrupt the circuit, thereby preventing electrical shock hazards and minimizing equipment damage. Now let's consider the scenario where the overcurrent protection is sized under 200% of the conductor ampacity due to specific application requirements such as motor circuits or circuits with intermittent loads. In such cases, the supply conductors are sized according to the duty cycle or the specific application requirements. However, the equipment grounding conductor must still be sized based on the rating of the overcurrent protection device, as dictated by NEC Table 250.122. This requirement can indeed lead to a situation where the equipment grounding conductor is larger than the supply conductors. This might seem counterintuitive, but it is a deliberate safety measure. The reason for this seemingly oversized EGC is that it must be capable of safely carrying the maximum fault current that the overcurrent protection device allows to flow during a fault condition. Even if the supply conductors are sized smaller due to the duty cycle, the potential fault current is still determined by the OCT rating. Therefore, the EGC must be able to handle that fault current without overheating or creating a significant voltage drop. Now, let's examine NEC Table 250.122 in more detail. This table provides the minimum size requirements for equipment grounding conductors based on the rating or setting of the overcurrent protection device in the circuit head of the equipment. The table specifies the minimum size of copper, aluminum, or copper-clad aluminum conductors for various OCT ratings. It's important to note that these are minimum sizes, and in some cases, it may be necessary to increase the size of the EGC to meet other requirements, such as minimizing voltage drop or ensuring adequate mechanical strength. For instance, consider an overcurrent protection device rated at 100 amps. According to Table 250.122, the minimum size for a copper equipment grounding conductor would be number 8 AWG. If the OCT rating is increased to 200 amps, the minimum size for the copper EGC would increase to number 6 AWG. As the OCT rating increases, the required size of the EGC also increases to accommodate the higher potential fault current. In this specific case, where the overcurrent protection is sized under 200%, the EGC sizing is still governed by Table 250.122. Based on the actual rating of the overcurrent protection device. So, Even if the supply conductors are sized smaller to accommodate the duty cycle, the EGC must still meet the minimum size requirements dictated by the opt rating. To further clarify this concept, let's consider an example. Suppose we have a motor circuit where the motor full load current is 20 amps. According to NEC section 430.22, the minimum size of the supply conductors would be 125% of the motor full load current, which in this case would be 25 amps. Let's assume we select number 12 AWG copper conductors, which have an ampacity of 25 amps according to NEC table 310.15. However, the overcurrent protection for this motor circuit is sized at 150% of the motor full load current, as permitted by NEC section 430.52. This would result in an opt rating of 30 amps. Now, according to NEC table 250.122, for an opt rating of 30 amps, the minimum size for a copper equipment grounding conductor would be number 10 AWG. In this case, the number 10 AWG EGC is smaller than the number 12 AWG supply conductors. However, if the overcurrent protection was sized at, say, 60 amps, the minimum size for the copper EGC would be number 8 AWG, which could potentially be larger than the supply conductors depending on their ampacity and the specific installation conditions. It's also important to consider the different types of equipment grounding conductors that are permitted by the NEC. These include Y-type EGC, which are typically copper or aluminum conductors installed in the same raceway or cable as the supply conductors. They also include metal raceways such as rigid metal conduit, intermediate metal conduit, and electrical metallic tubing, which can serve as equipment grounding conductors if they meet certain requirements. Additionally, the NEC permits the use of the metal armor of armored cable and the metal sheath of mineral insulated cable as equipment grounding conductors under specific conditions. When using metal raceways or cable armor as equipment grounding conductors, it's crucial to ensure that they are properly installed and maintain continuous electrical continuity throughout their length. This typically involves using approved fittings and connectors that are specifically designed for grounding purposes. In addition to sizing the equipment grounding conductor correctly, it's also essential to ensure that it is properly connected to the equipment enclosure and the grounding electrode system. The connection to the equipment enclosure should be made using a listed grounding connector or lug that is suitable for the size and type of conductor being used. The connection to the grounding electrode system should be made at a central grounding point, such as the grounding busbar in the electrical panel. This ensures that all equipment enclosures are effectively grounded to the earth, providing a low impedance path for fault current to flow back to the source. Furthermore, it's important to note that the equipment grounding conductor must be installed in the same raceway or cable as the supply conductors. This is to minimize the impedance of the ground fault path and ensure that the overcurrent protection device operates quickly and effectively in the event of a fault. Installing the EGC separately from the supply conductors can significantly increase the impedance of the ground fault path, which can slow down the response time of the opt and increase the risk of electrical shock. In summary, when sizing equipment grounding conductors under 200% overcurrent protection, it's crucial to adhere to the requirements of NEC Table 250.122. The EGC must be sized based on the rating of the overcurrent protection device, even if this results in an EGC that is larger than the supply conductors. This is necessary to ensure that the EGC can safely carry a maximum fault current that the opt allows to flow during a fault condition. Additionally, the EGC must be properly installed and connected to the equipment enclosure and the grounding electrode system to provide a low impedance path for fault current to flow back to the source. By following these guidelines, you can ensure the safety and reliability of electrical systems and minimize the risk of electrical shock hazards. Let's further expand on the practical implications of properly sizing and installing equipment grounding conductors, particularly in scenarios where the overcurrent protection is intentionally sized below 200%. This practice is commonly employed in applications involving motors, transformers, and other specialized equipment where specific operating characteristics necessitate a lower opt setting. In such cases, a thorough understanding of the NEC requirements and the underlying principles of grounding is paramount for ensuring electrical safety and code compliance. When dealing with motor circuits, for example, the overcurrent protection is often sized to protect the motor against overload conditions rather than short circuits or ground faults. The NEC allows for higher up settings for motor circuits to accommodate the motor's inrush current during startup. However, the equipment grounding conductor must still be sized based on the op rating as dictated by Table 250.122, even if the supply conductors are sized smaller to match the motor's running current. This ensures that the EGC can handle the maximum fault current that the op might allow to flow during a ground fault condition. Similarly, in transformer circuits, the overcurrent protection is typically sized to protect the transformer against overloads and internal faults. The NEC provides specific rules for sizing ops for transformers, depending on the transformer's impedance and other factors. Again, the equipment grounding conductor must be sized based on the op rating regardless of the size of the supply conductors. This is crucial for preventing dangerous voltage buildup on the transformer enclosure in the event of a ground fault. In addition to these specific applications, there are other situations where the overcurrent protection might be intentionally sized below 200%. For instance, in circuits supplying sensitive electronic equipment, it might be desirable to use a lower oct setting to provide better protection against voltage surges and other electrical disturbances. In these cases, the equipment grounding conductor must still be sized according to Table 250.122 based on the actual op rating. It's also important to consider the impact of long circuit runs on the sizing of equipment grounding conductors. In long circuits, the impedance of the conductors can increase significantly, which can reduce the effectiveness of the grounding system. To compensate for this, it might be necessary to increase the size of the EGC to reduce its impedance and ensure that it can effectively carry fault current back to the source. The NEC provides guidance on calculating voltage drop in circuits, and this information can be used to determine whether the EGC needs to be upsized to compensate for long circuit runs. Furthermore, it's essential to pay attention to the quality of the connections in the grounding system. Loose or corroded connections can significantly increase the impedance of the ground fault path, which can compromise the effectiveness of the grounding system. All connections in the grounding system should be made using approved connectors and fittings, and they should be regularly inspected and maintained to ensure that they are in good condition. In addition to the NEC requirements, it's also important to follow industry best practices when sizing and installing equipment grounding conductors. This includes using high-quality materials and components, following manufacturer's instructions, and conducting thorough testing and inspection to verify the integrity of the grounding system. It's also advisable to consult with a qualified electrical engineer or contractor to ensure that the grounding system is properly designed and installed to meet the specific requirements of the application. One area that sometimes causes confusion is the distinction between equipment grounding conductors and grounding electrode conductors. Equipment grounding conductors, as we've discussed, connect non-current carrying metal parts of equipment to the system grounded conductor or the grounding electrode conductor at the service equipment. Grounding electrode conductors, on the other hand, connect the service equipment to the grounding electrode, such as a ground rod, metal water pipe, or concrete encased electrode. The sizing requirements for grounding electrode conductors are different from those for equipment grounding conductors, and they are specified in NEC section 250.66. It's important to understand the difference between these two types of conductors and to ensure that they are both properly sized and installed according to the NEC requirement. Finally, it's worth noting that the NEC is constantly evolving to keep pace with changes in technology and industry practices. It's essential to stay up to date on the latest NEC requirements and to ensure that all electrical work is performed in accordance with the current edition of the code. This can involve attending training courses, reading industry publications, and consulting with experts in the field. By staying informed and following best practices, you can help to ensure the safety and reliability of electrical systems and minimize the risk of electrical hazards. The role of the equipment grounding conductor in ensuring electrical safety cannot be overstated. It is a critical component of the overall grounding system, and its proper sizing and installation are essential for preventing electrical shock hazards and minimizing equipment damage. By following the NEC requirements and industry best practices, you can help to create a safe and reliable electrical environment for workers and the public. Remember, electrical safety is everyone's responsibility, and it's important to take the time to learn about the principles of grounding and to follow the proper procedures when working with electrical equipment. By doing so, you can help to prevent accidents and save lives.